All right, this is 1.2 derivatives continued. Remember, this is the slope of the tangent line at a point or x value for dealing with functions. Anyway, let's start off with a warm-up. Okay, we did a warm-up in the last video. That should have been very similar to this. Again, want you to evaluate this limit here. In fact, it's easier than the previous video. I am going to add one more part to this problem. Okay, and I kind of gave the answer at the beginning of this video, and of course you watched the last video, you have the answer. I also want to ask is, what does your answer represent? That's another thing I want you to answer as well in this warm-up. Don't need to write a 5-paragraph essay or anything. Just write a sentence or two explaining what it does. Okay, so pause. What does it represent? So pause the video and give it a shot. If you're confused, again, I'm not going to explain the whole process here. We've been watching the last video, but this should actually be an easier problem than what was given in the last video. So pause the video, do it, and then pause and go through it together. Okay. All right, assuming you tried it, let's go ahead and start here. So again, right, f of x plus delta x, right? That's just going to be 2 times x plus delta x. Again, I'm doing it step by step or piece by piece here because this really confuses students. How do I get f of x plus delta x, and then f of x, even though they know what f of x is, they still kind of get confused. So I'm just reiterating here. Of course, the more and more you do this, the more you can just automatically just put it into this form. Okay, but for now, I'm just gonna, since we're just starting, okay, I'm just gonna do it step by step. So then, f of x plus delta x, we plug in x plus delta x into f of x, right, in for x, so 2 times x plus delta x is f of x plus delta x. And then f of x, of course, given to us is just 2x. So now, we have limit delta x approaches 0 of 2 times x plus delta x minus 2x over delta x. And then limit delta x approaches 0, 2x plus 2 delta x minus 2x over delta x. These should cancel. And then we get limit as delta x approaches 0 of 2 delta x over delta x. These delta x's should cancel. And then we get limit as delta x approaches 0 of 2. And then, again, this is 2 times, technically, delta x to the 0 power. So we plug in delta x in for 0. Doesn't change anything because 0 power. It'll be 0. It'll be 1. Okay, so 2 times 1 is 2. So this is our answer. Okay, so hopefully we got 2 for this. Okay, so what does your answer represent? So what does this u represent here? Again, I'm not really trying to trick you here, but again, according to the last video, what I said, again, this gives us the slope function. So at any value x, any x of f of x, if we plug in any x value into this, it'll give us the slope at that point. So we plug in any x value into f prime of x. Again, we're going to talk a little bit more about prime notation. This for f prime of x is just your slope function here. You plug in any x value, in this case, you will get 2. So your slope is always 2. And hopefully this makes sense, okay? Because if you draw out this function here, okay, why am I using this crazy pen again? If you literally draw this out, okay, let's say that this is what? F of x is 2x, right? Let's say that this is... Why is it not switching my color? I like to make my videos colorful. Okay. Say that this is like 2x. approximately. Okay, this is 2x, right? So this is, right, f of x, and f of x equals 2x. This is our line. Well, hopefully you know that this is in y equals mx plus b, right? This is, right, like our y equals 2x plus 0. This is our m. Our m is 2. Our slope is 2. Well, if we look at any x value here, 1, 2, 3, dot, 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 5,000, I don't know, 5,001, negative 8,000, whatever, right? Keeps going. The slope of y equals f of x equals 2x is always 2. So at any point, the slope is always going to be 2. Any point, slope will always be 2. So don't overthink it. Slope is always 2. Right? So this shows, again, that it works, right? At any x value, slope is going to be 2. And that makes sense because our function is literally f prime of x equals 2. So 2, 2, 2, 2, 2, 2, 2, 2, 2, everywhere, slope is going to be 2. Okay? Fun problem. So now let's get into that derivative notation. In the last video, I kind of went over the prime notation here. It's called, I mentioned it's called Lagrange's notation. We also have 3 other notations, but we're really going to focus on Lagrange and Leibniz's notation. These are not really used as much unless you're doing maybe some certain physics and stuff like that. But we're going to focus mostly on Lagrange and Leibniz's notation. I just kind of want to show you guys Newton and Euler's notation. We're going to focus mostly on Lagrange and Leibniz's notation. FYI, Newton and Leibniz are essentially the founding fathers of calculus, although there's arguments as to who discovered it first and all that. We're not going to get into that today. Maybe for a bonus video, we'll try to do that. But for now, let's focus on Leibniz and Lagrange. Let's focus on these 2 notations. Okay, so again, f prime. Okay, f prime of x. This is the first derivative. So essentially, it's doing that f of x plus delta x, whatever, that limit, one time. That's f prime of x. What do you think is going to be if we do that f of x plus delta x, that limit, right? That limit here, I'll show it to you again. This limit, f of x plus delta x minus f of x over delta x, limit is delta x over to 0. If we do that again, this will just be f double prime of x. Okay, 3 times f triple prime of x. 4 times f 4. No, it's not this. Okay, I was just trying to, we don't want to write all this for how many times we do the derivative, or in this case, that limit that gives us the slope function. Okay, again, it's also called the derivative. Okay, why don't we just say derivatives from now on? Okay, derivative is just the slope function. Okay, this is the derivative of 2x. Derivative of 2x is 2. We found that using this limit right here, which gives us derivative. Okay, so I'm just going to say derivative now, but just know that's the slope function. Okay, so if we do it 4 times, okay, we do more than 3 times, we start getting into this. We literally just start writing the number, but with parentheses here. Okay, we don't write f4 of x because then people think, oh, we're putting it to the 4th power. No, just use parentheses here to distinguish. So we're doing that, the derivative 4 times. It's just f4 of x, or the 4th order derivative. And then 5x, 5 times 6 of x, dot, dot, dot. Okay, so very straightforward. This is really straightforward derivative notation. This is really the most straightforward one. That's why I went with that one in our first video. So Leibniz's notation, it's not too crazy. It's just kind of weird at times. So again, that f prime of x here, okay, f prime of x is going to be dy dx. Okay, well, assuming y equals f of x, of course. You can also, in this case, I'm going to write it as d dx of f of x. Okay, so the derivative, remember, is an operation. Okay, this d dx, okay, derivative with respect to x. Okay, we do, in this case, because we've not learned implicit differentiation yet. Okay, we're just going to assume we're doing the derivative with respect to x with everything. Okay, so if that sounds confusing for now, that's okay. Okay, so this d dx, this derivative is an operation. It's d dx of f of x. Okay, so this f prime of x is done by doing the derivative with respect to x of f of x. That gives us f prime of x. Okay, so then we do the derivative twice. F double prime of x, that's just going to be, okay, this one is kind of weird. It's d squared over dx squared of f of x. Okay, really weird, but again, there is kind of reasoning to this, but I'm not going to get into that in this video. Kind of, like, but it's, it's some people say it's because you have to write less or something like that and other stuff, but for now, just make sure you know it. But like, so really, fn of x, so the nth derivative, n times you're doing the derivative, just know it as dn over dx to the n of f of x. Okay, or again, like if y equals f of x, d squared, or d, in this case, it can be d squared if you're doing the derivative twice, dn x by d over dxn. Okay, so one kind of common misconception here is that this d and this x, these are not like x is a variable, but this d, you can't, it's not like d times x. Okay, this is an operation. Okay, so d dx of, like, d dx, you can't just cancel the d's. This is not equal to 1 over x. Okay, this is an operation. Okay, it's kind of like a plus sign, right? Like a plus sign. This is an operation. Minus sign is an operation. You can't like misread it for something else. I don't know how you could in this case, but d dx you can. So don't cancel stuff out. D is not a variable. D is just operation. Okay. So, but it's in the form of variable, but it's not a variable. So d dx, this is like operation, right? And we do it of something, right? Like of f of x, right? Okay. So for example, if we have in our first video, like f of x equals x squared, we want to find the derivative of f of x. So we just do just like how we multiply on both sides. Again, this is not multiplication, not d dx times f of x, it's of f of x. We're literally just going to do d dx of both sides. We're literally just performing derivative on both sides, like multiplying on both sides, except this is not multiplying. This is, again, derivative is its own operation. So then you'll get f prime of x. And in this case, again, you do a limit definition, or you do that limit. Again, it's called the limit definition of the derivative. The limit definition of finding the slope function, which is the derivative. This is 2x. Again, I know this because there's shortcut rules, which we're going to get into in another video. But for now, if you ever need to find derivative, right, you just use limit definition. Okay, make sure you know this limit definition. If not, you can do a quick derivation like I did in the last video. But yeah, so this kind of wraps up derivative notation. I assume you're gonna, you know it. Yeah, so expect to, like, when we in future videos we'll have examples that put either of these notations again. I think this is the more straightforward one, but we will still see stuff in this notation. So make sure you're familiar with both. Okay? And make sure to ask questions in the comments if you're a bit confused. Okay, so now I just want to get into another thing here. This is just called the alternative form of the derivative. It's just another way of writing the limit as delta x approaches 0 of x, f of x plus, and then this is not x, limit as delta x approaches 0 of c plus delta x minus f of c over delta x. Okay, and now what I mean by that is if we say that f prime of x is equal to the limit as delta x approaches 0 of f, or by the way, this should be f, of f of x plus delta x minus f of x over delta x again. This should make sense. Well, if we want to find, again, this x, specifically, we plug in something for x. So if I plug in c, which is some value, some real number, we'll get f prime, okay, f, because again, this should give us the derivative at any x value. So if we do f prime of c, that's just going to be the limit as delta x approaches 0 of f of, and again, c is replacing our x here, so this will be c plus delta x minus f of c. Right, again, we're putting in c in for x, all over delta x. Okay, so another way of writing this, I'm not going to get into the whole derivation, is this. This is the same, this guy is the same as this guy. Now, you don't have to know this. There are certain cases where it's helpful. For now, like, I think this is good enough, right? You're trying to find derivative at a point, slope at a point. This could be helpful in certain cases. Also, if you're doing AP class, there could be certain multiple choice and stuff that puts stuff in this form, and you're just supposed to recognize it. So I'd just say kind of just know this, be familiar with it. But if you're asked to find derivative at x equals c, you can use this as well. But for now, I'd say just focus on using this limit definition. And of course, we'll learn later that none of this will be used anymore because they're the shortcuts. But again, when starting to learn derivatives, it's really important that we use these definitions. Okay, so just want to show you this alternative form of the derivative, that there is another way of presenting this. Okay, but again, you can use this if you want. All right, so that wraps up 1.2. Hopefully you find this interesting somewhat.